In this video, we'll discuss the problem, get special nodes in a directed graph in level order. We'll start by understanding what the question is asking, then we'll talk about a conceptual approach, and lastly we'll jump into the code. Okay, so this question provides us with three inputs. We have a graph, which we can see here on the left in green. We have the start node, which in our case is going to be the 3 node that's on the bottom left portion of the screen. And lastly, we have the special nodes array, which you can see on the top left of the screen. What we need to do is return all of these special nodes, an array containing all of the special nodes in level order. To figure out what that ordering is, let's start by just doing a level order traversal of this graph, starting at the 3 node. So we're going to start at 3, and then we go level by level. So the next is the 9 node, and then the 2 node. And now we go to the next level, which is the 1 node, and the 14 node, sorry. And then we go to the next level, which is the 7 node here. We've seen that before. What's unique about this question is we only care about nodes who are special nodes. We only want to pick out those nodes. So let's go ahead and cross out every node that isn't a special node. The 3 node is a special node. We can see it right there, so we don't cross it out. The 9 node is not a special node, so we cross it out. The 2 node is a special node, so we can leave it. The 1 node is a special node, so we can leave it. The 14 node is not a special node, so we cross it out. And the 7 node is a special node, so we can leave it. Okay, so to get the output for this question, all we need to do is take these numbers, the ones that have not been crossed out, and put them in an array. So the correct output would be the array containing 3, and then 2, and then 1, and then 7. And that's all. So that covers what this question is trying to get us to do. Now let's talk about how we could actually implement this. So we know that we will need to execute a level order traversal, which we know that we can use a Bfs to do that. Then we have to add this special caveat, which is only process the special nodes and add them into the output. To get us started, let's just write a level order traversal, a standard level order traversal with nothing fancy. So what we want to do is the very first step is always fill our queue with the first node. So let's say we can just say fill the queue with the first node or with the start node. I'll just write start. Then we want to say continue iterating while the queue is not empty. So we can just say while the queue has elements in it, we want to continue iterating. This is standard Bfs is all we're writing right now, the pseudocode for. In here, we want to say, all right, remove 1 node from the queue so that we can do something with it. Then you want to process that node. This part will change between different Bfs implementations. So I'll leave that blank for a second so that we can keep this as very generic Bfs code, pseudocode. And then the next thing is you want to add any neighbors or children to the queue. That just means any nodes that you can access from our current node. So add neighbors to the queue. So as an example, if we're on the 9 node over here, then the child of the 9 node is the 1 node right here, so you would add that to the queue. So we covered the standard Bfs. Now, the important part of this question is, what do we want to do at each node? Well, each node, we want to check if it's a special node. And if it is, we can add it to our output. And if not, we just don't do anything. We just move on. So we can just write right here, if is a special node. Right? If the current node is a special node, then add it to the output. Otherwise, we don't have to do anything. So we can just say add to output. Okay, and yeah, otherwise we don't have to do anything. And this covers the core of this algorithm. And you can notice the only part of this question that really takes thinking, if you already understand a Bfs, is just this one line of pseudocode here, right? Because the rest of it is just using the standard Bfs formula that we repeat over and over again. There is one remaining question, which is how do we figure out if a node is a special node? We could just grab, let's say the 14 node right here, And if we want to figure out if it's a special node, we can iterate through the special node and say, okay, starting at 7, is that 14? No. Go to 3, is that 14? No. Go to 1, is that 14? No. Go to 2, is that 14? No. So we can figure out, all right, 14 is not a special node. But there's a more efficient way to do it. If we did it this way, we have to iterate through the whole special nodes array at every single iteration of our loop, and that's not the most efficient. Instead, we can make a set out of this special nodes array, and with a set, you can check if a particular value is in the set in constant time instead of linear time with respect to the length of the array. So let's add a step at the beginning that's just going to be convert a special nodes, I'll abbreviate that as SN, to a set. And this covers really the core algorithm for this question. So let's go ahead and walk through it to see it in action. So we want to set up our queue over here so that we can see which nodes are being added and removed. And then we also need to have our output here so that we can build the correct output and make sure that we do get the correct output. Okay, so the very first thing we do if we go through our pseudocode is we convert our special nodes to a set. So right here, let's make a set that will contain the same nodes, but I'll use these curly braces to show that this is a set. It's not just a normal array. Now we want to fill our queue with the start node. So the start node is the 3 node in our case. So we come in here and we add 3. Now we want to start our loop, and we will continue iterating until this condition is false. Clearly the queue right now is not empty, so the condition is true. Then we enter the loop and we say, all right, let's remove the node at the beginning of the queue. So we take out the 3 node. We want to see, is it a special node? And if we come here, you can see that it is in our special node set. So we can add it to the output right there. We also want to add any neighbors of this 3 node to the queue. So that's going to be the 9 node and the 2 node. So let's add them right here. 9 and 2. That completes the first iteration, so we can go to the next iteration of our loop. What we want to do here is pull out another node from the queue, so we'll pull out the 9 node. We want to ask ourselves, is the 9 node in our special node set? It is not, so we can go ahead and erase it. We don't have to add it anywhere. And the last thing to do before we move on is add any neighbors of the 9 node into our queue. So we want to add the 1 node into the queue, right here. Now that completes another iteration, so we go back to the top. We pull out another node, which gives us the 2 node. Now we ask, is 2 a special node? You can see that it is. So we add it over here to the output. Now, before we move on, we need to make sure to add any neighbors of the 2 node onto the queue. So we'll add the 14 node right here because it is a neighbor of the 2 node. You can go from 2 to 14 with this edge. Now we go back to the top of our queue and we say pull out another node. So we'll grab the 1 node and we move it over here. We move it out here and we want to see, is this a special node? It actually is. We can see that it's a part of the special node set. So we add it to our output. So we can add our comma here. And then we want to add any neighbors of the 1 node to our queue. So we'll come here and we'll say, all right, add the 7 node. That finishes this iteration. We come up here to the 14 node, we pull it out. Oops, not with the commas. We just want the 14 node by itself. Okay, we pull it out here. We want to check, is it a special node? It is not, so we can go ahead and erase it. We don't have to put it anywhere. And we have to make sure that we add any children or neighbors of the 14 node. There's actually nowhere you can go if you're currently at the 14 node. So we don't have to add any children or neighbors onto the queue. Okay, that completes this iteration. Now we go to the next iteration. We pull out the 7 node. We check, is it a special node? Yes, it is. It's present in our set. So we move it to the output right here. Now the last step is to make sure we add any neighbors of the 7 node to the queue. Again, the 7 node, like the 14 node, doesn't have any neighbors, right? There's no arrows going outwards from the 7 arrow. So there's nowhere that you can go from the 7 node. So that means we finished this iteration. Our queue is now empty, right? All we have is these commas. Obviously, these don't mean anything. So we're complete with this, and we've gotten the correct output, the same as the output we have on the top right of the screen. Okay, so that hopefully convinces you that the algorithm works. And let's go ahead and talk about the complexity of this solution now. So let's grab a color. All right, the very first thing we want to do is define our variables. So we, like a standard graph, we're going to have V and E. So V is going to be the number of vertices in our graph. E is going to be the number of edges in our graph. But there's actually one other thing that matters here, which is that we are dealing with this special nodes array, and the length of the special nodes array actually does matter. So let's add that as another variable. We'll call it S. Let's say length of, and I'm going to abbreviate again, so we'll call this Sn. But we know that this is the special nodes array. Now that we have our variables, let's talk about what the time and space complexities are. So both of these should be pretty familiar to what we already know. If we just focus on the BFS part of the algorithm at first, we know that the time complexity is O of V plus E, and the space complexity is O of V. Let's start with the time. The reason we have a V is because every vertex, every node, has to be added to the queue at some point in time. So the time complexity has to depend on V. But it also depends on E, because we are traversing every edge, right? When we're at the 3 node, we go through all of its edges. So for every node, we go through all of its edges, which means in total, we go through every edge. So we get this O of V plus E time complexity of a standard BFS. The space complexity is O of V, because if you think of the worst case scenario, if you have like a central node like this, and then a bunch of nodes that are connected to it, if this was your graph, then after you process the central node, if that was your start node, every vertex in the graph, minus 1, would be in the queue at the same point in time. So you would have O of V minus 1 space, which is just O of V, because we can drop the constant. So that explains the standard BFS time complexity. But there's a little bit more nuance to this question. We have these 2 pink lines up here, like this line and this line. These are unique, and we also should be careful about how do they impact our time complexity. So this one down here is not affecting the time or space complexity, right? We're only storing one thing in the output, so that's constant space, and then in terms of checking if it's a special node, that happens in constant time with the set. But this line here is not so simple. To convert an array to a set, it actually iterates through the entire set. So that's going to be O of n time, where n is the length of that array. In our case, we're saying that the length of the special nodes array is called S here. So it's actually going to be O of S time for us to generate this set. So let's add that. So it's going to be O of V plus E plus S as our time complexity. And in terms of our space complexity, we are storing all of the vertices, and we're also storing S here, right? Because we're creating a set that has as many elements as the special nodes array. So we can write this as V plus S. One thing that is worth noting, though, is that special nodes, or S, will never be greater than V. Right? Because special nodes should only contain nodes that are actually in the graph. It doesn't really make sense if we had like 37 in the special nodes array for this graph, because there is no 37 node. So if we can assume that S is always going to be smaller than or equal to V, then we can drop it from the time complexity, right? Because if this, we could just replace it with a V instead of an S right here. Let me just scratch it out and put a V here. And if we did that, then we could just turn this to O of 2V plus E, which is just O of V plus E. So if we know that S must be less than or equal to V, which we don't necessarily know based on this question, so I would probably explain this in an interview and explain that it could be either way. But if we know that S is less than or equal to V, then we can just change this back to the original complexity, which is time is going to be O of V plus E, and space is just O of V, for the same reason. But if that condition is not given, then I think the more correct or precise time complexity is O of V plus E plus S, And the more correct or precise space complexity is O of V plus S. Okay, that's all for the approach. So let's go ahead and switch over to the implementation. Now, let's see an example of how to solve this question in JavaScript. To get us started, I've imported our queue, and we can see our example input and output right here. We can delete this comma. I've set up the skeleton of our function and a simple test case here just so that we can verify that our function works on the example. To get us started, the very first thing we need to do is we need to build our graph. We've seen this before. Our edges array isn't as easy to work with, so let's write this build graph function. It's going to take in the array of edges. We're going to create a graph, which is an object, and return that in the end. In between, we want to say iterate through each edge in our edges array. We want to grab out the start, and we can say start node and end node. Actually, let's just do start and end. Hold on, let's do that. Okay, so we have start and end. It's going to be the edge, and then we'll say graph at start dot push end. So we're saying create an edge that goes from the start node to the end node. But graph at start might be undefined, so we can't push into undefined. So let's real quickly just say if graph at start is undefined, which we can do like this, let's go ahead and just make it, let's make it an empty array like this so that we can push into it right here. Okay, so we've seen that before. That allows us to build our graph. Now let's set up our standard Bfs logic. So we're going to create a queue, which is a new queue. We're going to add the start node into the queue. We're going to write our Bfs loop, which is going to be so long as there are elements in the queue. So as long as the size is greater than 0, we want to keep iterating. Here we want to pull out a node by doing queue.dequeue. We'll process the node here. We'll come back to what this means in a minute for this question. We also want to grab our children or neighbors. Let's use neighbors this time. So we'll say graph at, not at start, at node gives us the array of neighbors. It's possible that neighbors is undefined, so we want to handle that real quick. So just if neighbors is undefined, let's just go ahead and continue. Meaning, there are no neighbors for this particular node. But otherwise, we want to iterate through each of our neighbors and add them to the queue. So we'll just say queue.enqueue the neighbor. Okay, so this covers the skeleton of a normal BFS. We haven't done anything too innovative here, or yet. Now we want to deal with the specifics of this question. So we know that we want to very quickly check if something is in the special nodes array. So we discussed in the approach that we can do this by creating a set. So we can say special node set is going to be a new set. And with the set constructor, you can pass an array like this. Special nodes is an array, and it will convert that down to a set. So this gives us a set so that we can check in constant time if a node is present in our special nodes. One other thing is that we also want to have our output array. So let's call that special nodes in level order, and that's just going to be an empty array. Okay, now we want to handle this part, line 40, which is how we process a node, meaning what do we want to do for every node in the graph? And we discussed what we want to do is, first of all, make sure that the node is in our set. So the way we do that is we put the set name dot has and then the node, the current node. So if the current node is in the set, we want to add it to our output. So we can say special nodes in level order dot push the current node because it is a special node and we just hit it in our level order traversal. So let's add it to that output right there. If not, we don't need to do anything here, and we can just go ahead and move on and add our neighbors or children to the queue. Okay, so just to be clear, a lot of this code is very standard and won't really change across BFS questions. The only thing that's really unique to this problem is these two lines of code here, where we create our output and our set, and then these three lines right here, where we do our condition to figure out if the current node is in the special node set. Pretty much everything else here, building the graph, creating the queue and putting the start node, our while loop, pulling out of the queue and adding to the queue, all of that is very consistent across BFS problems. So this is really where the important thinking comes into play. All right, let's go ahead and verify that our solution works. So we can save here And our test is just declaring our three inputs, and it's invoking the function on them. So the output that we expect to see here is going to be an array that contains 3, 2, 1, and 7. Let's see if we get them. So we can come here, we're just going to execute this file, and we get undefined. Let's see, why are we getting undefined? Because we are not returning our output. So let's make sure we do that. Okay, now if we run it again, okay, 3, 2, 1, 7 is exactly what we expected to get here. So let's quickly discuss the complexity of this solution. So we want to set up our variables here. So we know that v is the number of vertices in our graph, e is the number of edges in the graph, edges in the graph, and then s is the length of the special nodes array. So we said that the time complexity is going to be O of v plus e plus s. And the space complexity is going to be O of v plus s. For our time complexity, we know it's O of v because every node is added to the queue at some point in time. We know the e must be there because for each node, right here, we're iterating through all of its edges, which means in total, we're going through all of the edges in the graph. And we know that we have the s here because we're creating a new set out of the special nodes set. For the space complexity, we know that the v should be present because in the worst case scenario, we could add all of the vertices or nodes in the graph onto the queue at one point in time, except for one node, but v minus 1 and v are the same thing in terms of complexity. And this set that we're creating here also has length O of s because it has one element for every node in the special nodes array. We also discussed how if s is definitely going to be less than or equal to v, which is a reasonable possibility, then we can just drop the s from both of these. But in a typical interview, I would write it out this way and just mention that, hey, it's if s is always less than or equal to v, then we can just drop that. It doesn't really matter. Okay, that's all for this video, and I'll see you in the next one.